And in this case, for a hybrid machine especially, we like to use an electric drive, which is uses a VFD or a variable frequency device that is able to change the frequency, and that changes how fast the motor runs. One of the big advantages to an electric motor is its efficiency. We really want to have an efficient design. We couple this with a gearbox, and especially we've looked at and been using a two-speed gearbox, which really will help accentuate some of the characteristics of an electric motor, which I'll review here in a second, that really optimize a VFD drive electric motor for excavation in both EPB and rock. You can see here this is a motor curve, and graphs are a little bit confusing sometimes. The two things that I want you to look at are the operational torque and for hard rock and EPB modes. So this green line here and this purple line up here. And what this is a traditional electric motor curve. Electric motors have something called a base speed. So if you just plug them into three-phase, they'll run at, let's say, 900 RPM. And they do that with constant torque throughout. And as it happens, EPB machines really they need a lot of torque. They're a big mixing machine, and you don't need that high cutter head speed. Again, that helps minimize settlement, as Doug mentioned a little bit earlier. As soon as we get into hard rock, we're not mixing through all that muck at the bottom. We're keeping it in a clean invert, but we want that disc cutter to penetrate, chip it off, and so it's really advantageous for us to spin that cutter head faster in order to meet our excavation needs, but our torque need goes down. For an electric motor, once we reach that base speed and go beyond that, we enter something called the constant horsepower range of an electric motor. So we can run the motor faster and thereby run the head faster, but our torque drops off. So this is another nice characteristic of an electric motor is they're very efficient compared to a hydraulic system. You aren't producing a lot of heat. And then just the basic characteristics of an electric motor really match very nicely the needs of a hybrid machine, where we're going to go from a high torque need to a high speed need. So this enables us to really match the drive system up nicely to the needs of the machine. So we've now conditioned the muck, removed the muck, and we need to get it out of the machine. On a hard rock machine, again, we're picking it up. In this picture, you can see right towards the bottom, we have a big pile of muck. Hopefully, if our buckets are working well, this has all been picked up. Brings it up to beyond spring line, then starts to slide down into a muck conveyor system. The big advantage is, again, efficiency. Belt conveyors, you just don't see the wear. You don't have things sliding past each other. It's the belt on rollers, so that you don't see high wear. Whereas a screw conveyor, you're basically pushing and grinding this material to bring it out of the machine. So in this system, whether we're dealing, again, primarily with rock, we're able to handle a high volume of material with very low wear, and again, it's high efficiency, so we aren't producing heat with friction. When we go to an EPB machine, since we have to be able to support that face, either to support the face or to keep water out, we need that pressure in there. And we do that by timing the advance of the machine with the volume of muck coming in to a screw conveyor that, since the muck is conditioned, it's filled up and you're able to form a plug that prevents water from permeating or pressure coming through the screw. It's a great system. It's a flexible system, as we can see here when we look at open and closed mode. The big disadvantage is the amount of wear that we see, so it becomes a high maintenance issue. It is flexible, and especially as we start to look at machines that are hybrid machines or might be going through a lot of mixed geology, we want to design the screw to handle that. Soil has a different swell than rock does. In rock, we're going to figure somewhere around 1.6, 1.7 range swell. So after it's no longer in situ, we have to handle a higher volume of muck than we would with soil, which is 1.2 to 1.3. Some ways we can handle this is by oversizing the screw for volume. The other way we can do this is to be able to run the screw a little bit faster since it's open. Anytime you run steel on steel faster, we're going to see higher wear. So in the screw design, we're going to take this into account by including wear plates that are replaceable, the life of the job, on the screw pipes, the casing liners that are maintainable, and then the ability to inject ground conditioning and detonite into that screw to help minimize wear seen there. What we can see here is we have the cutter head, but then behind the machine, we need to get a few different pieces of equipment installed, both a belt conveyor and a screw conveyor, which on these machines, obviously geometry and room becomes a big issue. The more equipment you put in there, the more difficult it is to work. And so we really need to pick and choose the features that we install in these machines based on what is needed for that job. And a lot of that is the size of the machine, how much room we have. In this particular case, this machine has a screw conveyor that's installed. The belt conveyor frame is in place. So we have right here is a screw conveyor that's installed for EPB operations. It dumps onto a belt conveyor, and the screw conveyor runs through the frame. When we want to move to a more of a hard rock application, we're able to pull that screw out and store it, and the belt conveyor is able to be extended into the chamber. We bring in a muck chute in order and modify the head with muck buckets in order to bring that muck out. So most of the equipment is in place, and it requires modification to the screw and bringing that muck or that conveyor forward. On a different design, if we have room, you can see here that we have both the machine conveyor installed and the screw conveyor installed at the same time. Here we're able to move the belt conveyor back and forth while keeping the screw conveyor in place during the full excavation. Part of this will require us to have a muck ring that's extendable and retractable. So into that bulkhead region, we're trying to fit a bunch of hydraulics, and really that helps to minimize the amount of time that we need in order to change the machine from one mode to another. With that, we've reached another poll question. What are the main factors that influence your decision to use a hybrid TBM? Is it the geology, the cost, the risk, or is it something that's in the contract specifications?
And here's another question for you, Brad. What are some of the current hybrid TBM projects Robbins is working on?
Usually we don't have percentage-wise in the design office now I'm speaking. They're kind of the lower percentage, but we happen to be working on two concurrently. They're both different, but one's a much larger hybrid TBM, has many of the features that you saw there with the extendable muck chute, screw conveyor, and a belt conveyor installed at the same time. We're also looking at another project. It's a little bit smaller, and there we're utilizing a center screw design. And again, this depends on our changeover time and the geometry that we have in place. But we're able to, again, extend the muck chute and retract the muck chute, but we don't have a belt conveyor that's installed at the same time. So in our office currently, we're working on two different hybrid designs. And again, they have some of the same features, but in order to work efficiently in the geology and that particular project, we're kind of picking and choosing the features that go onto those machines.
I'll just add a couple things there if I could, Brad. I mean, from the standpoint of future projects in which this type of machine or application of this type of machine can be used, It's actually, quite large. I mean, there's jobs in Singapore that require such a machine, Bangalore in India, where you have a very, very hard rock on the bottom. 200 MPa granite on the bottom, and that line of demarcation between the rock and the soil is right through the face. But there are large sections of rock and then large sections of soil. Even to consider even the project here in San Francisco, the metro there, we have large sections of rock where we don't need to be in pressurized mode, but we can certainly take advantage of the large rock sections to excavate at a good pace, a high pace. So primarily this machine type works well in metro applications because they aren't so deep and we have large sections of mixed face. So from an international standpoint, there are quite a bit of markets, if you will, that can use this type of technology.
All right. Well, thank you very much. I'm going to turn the floor over. Speaking of future markets and things that need to be developed, I'm going to turn the floor over now to Doug, starting off with remote cutter monitoring.
Thanks, Brad. Yeah, one of the things that we really need to consider when talking about EPBs or hybrid machines or really pressurized face machines is we have to have some method to monitor the cutters without physically going into the cutter chamber when you're under pressure. So these are enhancements we're working on as far as the engineering standpoint to take these EPB, slurry, hybrid machines, pressurized face machines, if you will, to the next level in regards to cutter change time, in regards to knowing what the cutters look like, knowing what your tool wear is. So some of the development or objectives we have within this field as far as cutters and cutter changes is we need to increase the TBM uptime by reducing cutter inspection time and change frequency. In classical rock technology, it's quite easy to go in there, and you have to every couple pushes at sometimes, depending on the hardness of the rock, to go and inspect your cutters. It's quite easy. You go and you crawl it through the cutter head chamber. You look at your cutters. The cutter head is typically fairly clean. You can wash it off fairly quickly and inspect your cutters. When you're in a pressurized face mode, you can't do that so easily. You have to have interventions, and sometimes the interventions can be, at a higher pressure where you have to. The men working in the pressurized chamber can only work for a short period of time. So we need to reduce that change, or we reduce that inspection frequency by basically having better quality cutters and discs and monitoring systems. Bearings and seals that outlast the several discs. We have to have, in this typical application of mixed face, we know that the cutters could stop turning and the discs start to wear down, and if we're pressurizing the cutters under 2 or 3 or 4 bar, we have to have a sealing system in those cutters that actually can compensate for that. We need high cutter loading. As we saw in that video, we can see these disc cutters take quite a bit of abuse when they go through hard rock. So we want to put big cutters with high disc loading and also high wear resistance. But we don't want those cutters to protrude out too far into beyond the faceplate of the machine. We want to have the ability to change the cutters under hyperbaric conditions, and so we're working with the hyperbaric people to see what could be done in that regard. And we want to be able to change the tools from soft to disc cutters with cutter handling and cutter devices to help us do that. And we have a big focus now on disc life, material development and disc life, not only on the cutters, the disc cutters, classical disc cutters, but also on soft ground bits. This is a typical application of a mixed-face hybrid type machine when you have cutter failure. When that disc fails, as it's in cutter photos on the left-hand side, going from a soft ground geology to a rock geology, that disc fails. You're not monitoring that disc, what eventually will happen is the cutter faceplate will make contact with the ground, and you're going to wear